Hi, my name is Mel, and the following presentation will explore Internet addressing, covering fundamental concepts, key differences between IPv4 and IPv6, address classes, subnetting, routing, security, and future developments. We journey from basic ideas to advanced addressing techniques essential for network management. We will cover the fundamentals of Internet addressing, public and private networks, IP address classes and evolution, CIDR, octets and hexets, subnetting, worked examples, routing and address resolution, and finally addressing security and future trends. Now, I will cover a lot of these topics in other videos as well. This is just sort of like a general sort of introduction. But like I make a lot of these sorts of videos. I'm covering everything I learned from my IT Cert 3, Cert 4 in cybersecurity, and like more advanced subjects as well. I'm doing the diploma next year, so will cover some of that as well. Not here, but elsewhere. Understanding what an IP address is, its necessity, distinctions between IPv4 and IPv6, and the structure and notation of IP addresses forms the foundation of Internet addressing. An IP address uniquely identifies a device on a network, enabling communication across the Internet. It acts like a postal address, ensuring that data reaches the correct destination in a network. Okay, so it is just exactly like that, all right? It's like making sure the data gets to it's where it's meant to be delivered to, all right? IPv4 uses 32-bit addresses, allowing about 4.3 billion unique addresses, while IPv6 uses 128-bit addresses, which allows several quintillion is a word, vastly expanding the address space to support growing internet demands and improved features. And that's really why we had to replace IPv4 and why IPv4 has to be replaced with IPv6, because we ran out of all the addresses quite some time ago. Some people still use IPv4, but look, mostly I would recommend anyone setting up something like to transition to IPv6 when they can. Because it gives like more features, it's more secure, easier to set up and understand as well. Okay. IPv4 addresses are expressed in dotted decimal notation, so like a full stop. Okay, like there's like a number, full stop, a number, full stop, with 4 octets. So octets are 8. So 4 groups of 8. While IPv6 are hexadecimal numbers, so that's 0 to 9, then A through to F. Okay, hexadecimal is 16, whereas IPv4 only uses 0 to 9. Okay, notation divided into 8 groups of 4 hex digits, and they're separated by a colon. Okay. So that's a difference. So a IPv4 address will have full stops, or dotted, as they call dotted decimal, in 4 octets, while IPv6 use hexadecimal, so that includes A through to F, right? Because it's 16, separated by colons. All right, just so that's a difference. The following section explains how IP addresses are allocated in public and private networks and the role of network address translation, or NAT, in enabling private networks to communicate externally. And I will fully flesh out NAT in another video, but I'm just going to cover it very briefly. Public IP addresses are globally unique, and they have to be, otherwise it'd be a clash, and allocated by regional authorities to ensure no conflicts occur on the internet, enabling devices to be reachable from anywhere in the world, which is what the internet's all about. Private IP addresses are reserved for use within local networks. So you're talking like companies or organization that have their own sort of like, they've got their own networks. Like the internet's just like a bunch of networks joined together, really. So private IP is for local and not routable onto the public internet. Common ranges include 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. Okay, so they're common private. So if you see an internet address like that, it's a private network, all right? It's something within that doesn't connect out to the wide, Brave New World sort of thing. Network address translation allows multiple devices in a private network to share a single public IP address, translating private addresses for external communication, enhancing security and conserving IP space. Because like IPs rapidly run out, and so we've run out of IPv4, which is why now everyone has to start making the way into IPv6. Like some still IPv4, but not, like it's not, that can't last, in my opinion. We will review the traditional classful IP addressing systems, its limitations, and how the transition to classless addressing, or the CIDR, CIDR, addresses these challenges. Classful addressing divided IPv4 addresses into 5 classes A through to E, based on fixed address ranges, with class A, B, and C used for host addressing, and classes D and E for multicast and experimental purposes. And class A has got the largest number of addresses available, and class C the least number. Okay, just so you know that. Classful addressing led to inefficient allocation and IP address exhaustion due to fixed block sizes, limiting flexibility and scalability for growing networks. Yep. CIDR, or classless addressing, okay, CIDR, introduces flexible subnetting and aggregation by allowing variable length subnet masks, improving address utilization and routing efficiency. Now this is for IPv4. You do not need to use CIDR, I don't think, for IPv6. CIDR, or classless inter-domain routing, transformed IP address allocation and routing by replacing fixed classes with flexible prefixes, enabling scalable and efficient use of IP space. CIDR was introduced to address limitations of classful addressing, reducing routing table size, and improve IP address allocation efficiency in the expanding internet. CIDR notation denotes IP prefixes using a slash followed by the prefix length, like /24, representing the number of the bits in the network portion of the address used for routing. Okay. CIDR enables routing aggregation, reducing the size of the routing tables and improving internet routing scalability while conserving valuable IP addresses. The following section explains octets in IPv4 and hexadecimal in IPv6 addresses, including conversions between decimal, binary, and hexadecimal numbering systems. Okay, decimal is 10, binary's just got 1 and 0, so 2, and hexadecimal is 16. An IPv4 address consists of 4 octets, each an 8-bit segment represented in decimal from 0 to 255, structured as dotted decimal notation for readability. So we would call that probably also a full stop, but it's called dotted decimal, just so you know. IPv6 addresses are made up of 8 groups of 16-bit segments called hexets, represented in hexadecimal notation, separated by colons for compactness and clarity. Understanding how to convert IP address components between decimal, binary, and hexadecimal formats is crucial for subnetting, routing, and troubleshooting network issues. And there's any number of tools like that you can convert, like online tools, free tools you can use to do this so that you don't have to try and do your head in. Probably not such a bad idea to use the tools. Subnetting divides networks into smaller segments to improve organization, security, and performance. We explore subnetting basics and calculations for both IPv4 and IPv6. I did do a separate video on subnetting, but we'll cover it briefly here too. Subnetting helps organize network usage by segmenting a large network into smaller subnets, reducing broadcast traffic and enhancing security and management. Yeah, you should always subnet, I think, in my opinion, because it does help reduce attack surface, and it does improve security, and it does help with management, and also reduces latency and lag in a network because you're reducing broadcast traffic. So I think it's a good idea. I really think you should be subnetting myself. Subnet calculation in IPv4 involves determining network and host portions using subnet masks applied to the 4 octets, enabling precise network segmentation. IPv6 subnetting uses prefix length applied to hexets, allowing flexible and hierarchical subnet design suited to modern networking needs. Yeah, look, IPv6 is way, way better than IPv4, quite honestly. It's much superior. Practice with real-world examples of IPv4 and IPv6 subnet calculations helps solidify understanding of address segmentation and troubleshooting techniques. This example works through calculating IPv4 subnet addresses by applying subnet masks to octets, defining network, broadcast, and host ranges. Okay, so what they're talking about a mask, I don't know if you've ever seen this 255.255. whatever, 255.255, you're going to do all 4. That's a subnet mask. You would like 255.255.255.0 is probably what you go for the smallest, and 255.0.0.0 is being the biggest. So the 255 denotes the network, and all the zeros is what the host uses. Okay, so the more you allow the host to use, the bigger your network can be, if that makes any kind of sense. We demonstrate IPv6 subnetting by manipulating prefix lengths and hexets, showing how to determine subnet boundaries and address spaces. Learn how to analyze address ranges for conflicts or misconfigurations and troubleshoot network connectivity issues related to IP addressing. Explore how IP addresses are used in routing, the role of ARP, Network Discovery Protocol, and how routing protocols leverage CIDR or classless inter-domain routing for efficient data forwarding. Routing directs packets based on IP addresses through the network. Accurate addressing ensures data reaches its destination via the optimal path. ARP resolves IPv addresses to MAC addresses, which is Media Access Control, MAC, within local networks, while Neighborhood Discovery Protocol performs similar functions for IPv6, enabling local communication. Yep. And I will talk more about ARPA Neighbourhood Discovery Protocol in another video. Routing protocol using CIDR aggregation to summarise routes, reducing routing table size and improving network efficiency and scalability. Okay, so CIDR aggregation does reduce or summarise multiple IP routes into a single route to reduce routing table sizes. And like reducing routing table entries improves network's performance and scalability. Yeah, it does do that too. And promotes efficiency. Yeah. The final section addresses best practices for secure addressing the impact of IPv6 adoption and future trends shaping IP addressing technologies. Yep. Implementing secure address practices, including proper subnetting, network address translation usage, and access controls, help protect networks from unauthorized access and attacks. Yep. IPv6 adoption enhances security features, supports a vast address space, and improves routing efficiency, driving the internet evolution and supporting emerging technologies. Yeah, look, I would really recommend that everyone go to IPv6. Maybe, you know, like do it in bits and pieces, but like you really do need to do it, okay? Because it's just going to be so much better. Emerging trends include increased IPv6 deployment, automation in address management, and integration with new protocols to support Internet of Things and cloud computing. Yep. Understanding internet addressing from fundamentals to more advanced techniques is vital for addressing network management. The evolution to IPv6 and CIDR ensures the internet can scale securely and efficiently into the future. Well, hopefully we can. Hope it does. Thank you for your time.